Good. So welcome everyone. Today we're very happy to have Thomas Mertens here, and he's going to tell us about Liouville and JT quantum gravity, holography, and matrix models. So Thomas, take it ahead.
So first of all, thank you very much for inviting me. So I will talk on some work that I did the past year. So I've written the archive numbers here and also some work in progress. So let me start by giving a brief outline of my talk. So first, of course, I'll give an introduction to the topic. And then I will discuss fixed length amplitudes in Liouville gravity. And that will be the main focus of my talk. And I will discuss the disk partition function, the bulk 1-point function and its relation to higher topologies, the boundary 2-point function, and then what I will call degenerate insertions, and I will explain that later on. And then finally, some comments on the other amplitudes as well. And then near the end of my talk, I will mention two different perspectives on these calculations. One is in terms of a quantum group theoretic perspective, and the second one is in terms of a two-dimensional dilaton gravity perspective. And then, of course, I will end with some conclusions. So let me start by first giving an introduction to this topic. So from Kitaev's 2015 talks, we learned about these SYK models, and in particular about their universal low-energy Jacques-Teitelbaum, or JT, gravity description. But since then, we have learned that JT gravity is very interesting in its own right. And it provides for a non-trivial and solvable holographic model of 2D quantum gravity, and these are, well, very rare. And since then, many developments have been realized in this model. So for instance, we know the full classical solution of the model, including the coupling to quantum matter, and that has been important recently for the developments in the information paradox. We know of the exact quantum solution of correlation functions, of boundary correlation functions, and their interpretation in terms of bulk gravitational physics, such as shockwave scattering. And we also have learned very recently, during last year, about higher genus and multiboundary amplitudes and their role in quantum gravity. In particular, they are important to understand the very late time boundary correlation functions and also to explain the page curve through these replica wormholes, which are higher topological surfaces. So it would be interesting to extend our class of solvable models and see how generic some of these lessons are for quantum gravity. So the goal of my talk here is to discuss another model of quantum gravity, which is 2D Liouville gravity. And I will, well, discuss its amplitudes, and I will phrase this discussion in the same language as we have done for JT gravity. And then near the end, I will interpret this thing as a quantum deformation of JT gravity, and also as a specific model of dilaton gravity with a hyperbolic sign dilaton potential. So first, let me give a lightning review of JT gravity itself. So Jacques-Teitelbaum gravity is a specific version of two-dimensional dilaton gravity. So I've written down the action here. And the dilaton potential is linear in the dilaton field phi, giving you this very specific coupling here. This +2 means that I have chosen a negative cosmological constant, and my bulk geometries will correspond to ADS2 geometries. And I have also added the Gibbons-Hawking boundary term here. Now, this theory has been solved exactly, and I will just present you some of the results. So the disk partition function was calculated a couple of years ago, which is a canonical partition function z of beta, and you can draw it graphically like this. So this is a boundary circle of length beta, the inverse temperature, and then the blue region is where quantum gravity lives. So you can exactly do the path integral of this gravitational theory, of this topology, and the result you find is this answer. So it's an integral from 0 to infinity over some variable k. There's a measure k times sinh 2 pi k, and then a Boltzmann factor e to the minus beta k squared. So, well, from this you see that the energy variable is just k squared. And it is interesting for later during my talk to briefly mention that the semi-classical limit of this object, or the thermodynamic limit, which is just the saddle approximation of this integral. So at high energies, where we can use the thermodynamic limit, the spectral density that you can see from this, it has Cardy scaling. It goes as e to the 2 pi square root e. And then you can compute the saddle of this integral, and you get square root e is proportional to the temperature, the Hawking the temperature of the system. And this matches with the black hole first law of mass versus Hawking temperature for a classical black hole in JT gravity. So you classically solve the equation of motion associated with this action, you find the black hole solution, you compute the total mass, you compute the Hawking temperature, they satisfy the same relation that you find here as the saddle of this thing. So this thing generalizes it. It's not just a saddle, it contains quantum gravity fluctuations as well. The second object that I will need for later on in my talk is the boundary two-point function. So imagine I have some boundary CFT matter sector that's being coupled to this gravitational theory. And this boundary CFT, it has matter operators OH of tau that I've written here. And then I compute the boundary two-point function. So I have these two boundary operators here. And again, I do the path integral over the full gravitational theory, over the full JT gravity theory. And this was computed by several works in the past few years. And this is the answer you get. So it has a double integral over two k variables. And again, we have the same measure that we had for the partition function. We have these Hamiltonian propagation factors, or Boltzmann factors if you want, where this tau is short for tau2 minus tau1. So it's the distance along the boundary on one side of the two operators, and then beta minus tau is the distance, for instance, here on the other side. And then you have this last piece, which I will call the vertex function. And this is a bunch of gamma functions. And by these plus minus symbols, I mean that you have to take the product of all cases. So in the numerator, there's basically a product of 4 gamma functions here. And it's this piece that couples the K1 and K2 integrals together and makes the entire thing not trivial. Okay, and then last year we have learned about how to think about and compute multiboundary amplitudes. So this was done in the work by Satchenker and Stanford last year. So this is an example of an amplitude, of a generic amplitude. So I have n boundaries here, and they are connected through some higher topological geometry in the bulk. And then they showed that you can calculate the JT gravity amplitude associated to this object by doing this manipulation. So in this case, we have n integrals over the BI variables. So I have denoted these BI variables here. These are geodesic lengths of all of these tubes that connect the asymptotic boundaries to this interior higher topological object here. So you have n of those integrals. And then you have an object ZJT, which is a function of beta I and BI. So this is an amplitude associated to just these boundary tubes here. So from the B1, for instance, all the way to the asymptotic circle beta 1. And then there's also VGN of B. So now let me, in a bit more detail, describe all of the ingredients in this formula and where they come from. So this ZJT here, that's the single trumpet amplitude, and you can compute it explicitly in JT gravity, and it has this simple form. You can also view it as the disk partition function JT gravity with a specific defect in it labeled by B. Well, it's a hyperbolic defect in particular. So that's one ingredient here. Another ingredient is the integral and the measures itself. So the measure of that integral is dB times B, where B is the geodesic length, as I mentioned here, and this geodesic length ranges from 0 to infinity. But when you glue these exterior trumpets to this higher topological thing in the middle, you can glue these with a twist. So you can twist these tubes before you glue them. And you can, well, or this twist variable has a range from 0 to B, because you can twist all the way around the circumference. And that one just gives you an additional factor of B to make for the total measure dB times B. And then finally, you have this object here, VGN of B. And these are these famous Weil-Petersen volumes. Well, they are generically, well, they are multivariate polynomials in all of the BI squared. So they're functions of all of these B's that are here. And they compute the volumes of the moduli space of Riemann surfaces of genus G with n geodesic boundaries of length V1 up to Bn. And they are known recursively through Mirzakhani's work. So this is everything that I wanted to say about JT gravity. And I will discuss Liouville gravity next. And I will try to phrase the entire discussion in parallel to these amplitudes that we have discussed here for JT gravity. So again, the theory that I really want to study here is Liouville gravity. So what do I mean by this? By Liouville gravity, I mean the non-critical string that you get by coupling 2D gravity to a matter path integral, or alternatively by studying the critical string with the 2D Liouville matter and ghost CFT, coupled together with the conformal anomaly constraint that the total central charge should be 0. So in detail, what I mean by Liouville gravity is the Liouville action plus a matter CFT action plus the BC ghost action. So to be a bit more explicit, This is the Liouville action. So this is the standard way of writing it on some manifold sigma. The Liouville action is labeled by this parameter B that's in here. And well, this is standard notation in Liouville theory. So using that B, I have this number Q, where Q is B plus 1 over B. And then the Liouville central charge is 1 plus 6Q squared, which is bigger than 25 automatically. You can think of the Liouville action as arising from the conformal factor of the metric. If you think about this as a non-critical string, then the 2D gravity path integral, the conformal factor contains the physical information, and that phi field that's here in the conformal factor, that one is precisely the Liouville field. So that is one piece of the action. Then we have the matter piece. Now, for most of my talk, I will not assume anything about the matter sector, except that it's an arbitrary CFT with a central charge less than 1. The central charge has to be less than 1 because the Liouville one is already bigger than 25, and we need the total to be 0. And the ghost central charge is, of course, minus 26. But I would like to have two particular choices in mind. The first is we can take time-like Liouville CFT for the matter sector. This is just the usual Liouville where you replace B by IB, and this automatically gives you a CFT with central charge less than 1. Another option is to take the Q comma P minimal model. And in this case, if you solve this central charge equals 0 condition, you find that the Liouville parameter B is related to these two integers Q and P by B squared is equals Q over P. And then the full thing, so this minimal model plus Liouville plus ghost, is called the minimal string. And the reason that I will be interested in that is because this thing has a matrix model description, which I will exploit for the purposes of calculating these amplitudes. And then, of course, SGH is the usual BC ghost theory, as always. Of course, there is a generalization of this construction, which has been known also since the 80s, to the n equals 1 supersymmetric Liouville supergravity. And almost everything that I'm going to say can be generalized to the supersymmetric case. So you can take a look at the papers if you want to see some of the details, but I will largely only talk about the bosonic case in this talk. So, well, I will be in particular interested in holography, which means I will be mostly interested in having manifolds with a boundary, and I will need that boundary to have a fixed length. So, so I need these boundary conditions in my Liouville gravity. Now, for the Liouville piece alone, boundary conditions have been investigated in the past thoroughly, and the boundary conditions that we will need are these FCCT brane boundaries, and they were discovered by Fateev, Zamlodchikovs, and Teschner. And here I've written down the Liouville action again, but now supplemented by a boundary term, and that boundary term is characterized by that mu B parameter, which labels the specific FCCT brane that I want to consider. And that parameter mu B is called the boundary cosmological constant. Now, when viewing the theory as 2D quantum gravity, as I mentioned before, the Liouville field is actually related to the metric as just a conformal factor of the metric, which means that the boundary length, if I study this theory on a manifold with the boundary, is just this boundary integral of e to the b phi. So this is the boundary length computed in the Liouville metric. And now I want to transform my amplitudes to have a fixed length description. So that means that in the total path integral, I will take a Fourier transform of that boundary cosmological constant here times e to the minus action, because in the Liouville action, the mu b only multiplies the boundary length. So the integral along the boundary times e to the b phi, that's the boundary length. And now I multiply it by that and I take the mu b integral. That means I just bring down a delta function which restricts this total boundary length to the constant L that I prescribed before, which is inserted in the path integral. So we get a delta function on the boundary length, and this will be my definition of a fixed length amplitude in this theory. There is a generalization of this, which is to take a piecewise constant mu b, and that will allow a boundary with fixed length segments, L1 to Ln, and I will need that as well. Okay, so now that we know the types of calculations we will do, I want to think a bit about the operator insertions that will be interesting for my purposes. So I want to think about an amplitude with an arbitrary number of insertions of bulk and boundary tachyon vertex operators. So this is notation, of course, from string theory. So the amplitude that I have in mind is a disk amplitude. I have a bunch of boundary operators, B1, B2, and so on. They are separated by fixed length segments, L1, L2, and so on. And then also potentially a bunch of bulk operators, T1, T2, and so on. Now let's be a little bit more explicit about these operators. So for the bulk and boundary operators, we take the usual construction that you do in string theory. So these operators are diff invariant on the worldsheet, and you can write them as a worldsheet integral. So for instance, the bulk operator is a worldsheet integral of some matter operator. So this OM is an operator in the matter CFT that is being dressed by the Liouville operator e to the 2 alpha phi. So this is the generic parameterization of a Liouville operator that is conventionally used. And that Liouville operator on its own has a conformal weight that's alpha times q minus alpha. And then the weight of the matter operator here and the one of the Liouville operator that dresses it, they are related to one another by the fact that the sum is equal to 1. So this is the standard construction you do in string theory. And you have a very analogous relation for the boundary operators that I want to study. So again, you have a boundary integral of the manifold, a boundary matter operator being dressed by a Liouville boundary operator. The Liouville boundary operator will be labeled by a number beta, and that beta is related to the weight of that boundary Liouville operator in this way, with again the sum being 1. So there's nothing new here. This is just the standard way in which you construct vertex operators in string theory. So now let me summarize the strategy that I want to use. So I want to transform the Liouville gravity amplitudes to the fixed length basis, and I will focus mostly on disk diagrams that don't have worldsheet moduli or that don't have cross ratios. We do this because otherwise you get technical complications in the calculations, and in principle it should work out as well for the more complicated cases, but we don't yet understand these. So I'll just focus on the simplest kinds of diagrams that don't have worldsheet moduli. And on the disk, there are only 5 diagrams that satisfy that condition. This is the disk amplitude, the bulk 1-point function, the boundary 2-point function, the bulk boundary 2-point function, and then the boundary 3-point function. So I will discuss all of these, and in particular, I will focus on the first 3, and I will very briefly make a comment about the last 2. So computing these first 3 amplitudes, that will be the main part of my talk. And of course, I want to reinterpret these as thermal disk diagrams, where the total boundary length is beta, is the inverse temperature. And then the operators, for instance, in this last diagram, they are separated by Euclidean time differences. So I want to interpret these kinds of calculations as quantum gravity calculations. Now, I will also mention some comments or discuss a little bit multiboundary amplitudes without operator insertions in that case. And they do have worldsheet moduli, the tube length, that needs to be integrated over. But in this case, we can do it in some cases. In particular, the worldsheet calculation is possible for the 2-boundary amplitude. But once you have more than 2 boundaries, this is no longer possible. But then, of course, we have the solution. We can specify our matter sectors to the 2, p minimal model to get the 2, p minimal string, which has a single matrix model description. And then we can use these matrix techniques to get more general amplitudes. And that is the strategy we will use for these multi-boundary amplitudes. Okay, so now let's get started. So the simplest case is the disk partition function, which I have drawn here on the left. Now the disk partition function is known in Liouville theory. It was calculated 20 years ago by Fateev and Zamolodchikov, and also discussed after that by Seiberg and Shi. And this partition function looks like this. So it's basically cosh 2 pi s over b, where this s variable that I introduced here is related to mu b by mu b being the cosh 2 pi bs. And again, mu b is the parameter that characterizes or defines my FZZT boundary. I have this prefactor kappa here, so I've written it out here for completeness, and this mu factor here, but I won't be needing that during my talk, so you can ignore these for now. And then the strategy is to take this amplitude and transform it to the fixed length basis. So what I do is I just take this Fourier transform that I mentioned before, and I operate with this thing on this Liouville disk partition function with an FZZT boundary. And that should define for me the fixed length amplitude. Now, this integral mu b, it ranges along the imaginary axis. So it ranges along this green contour that we have here. And then the strategy is to contour deform this integral from the green one to the blue one, where the blue one wraps around the branch cut of the integrand. And well, the integrand itself is z of mu b, so it's cosh 2 pi over b times s, where s is defined as the r cosh of this mu b. So the integrand itself is this thing, And well, you can see that this thing indeed has a branch cut that I've drawn here from minus kappa to minus infinity. And we just need to calculate the discontinuity across this branch cut. And if you do that calculation, you find that it's basically the sinh of an arc-cosh. And after you have done that, so you have an integral over mu b from minus kappa to minus infinity, it is convenient to again do a substitution in that integral to write it as an integral over a variable s again, where s and mu b are related in this way. And in total, you get an expression that's very suggestive. You get an integral over s from 0 to infinity, e to the minus l kappa cosh to pi bs. So this was this mu b here. Sinh to pi bs, this one you get just by changing variables in the integral, and then sinh to pi over bs. And this last sinh is the one you got here from taking that discontinuity. So this expression is very suggestive, and there's lots of structure in it. And near the end of my talk, I will discuss on how you can read that expression. But for now, I want to mainly focus on extracting some of the physics that's contained in this kind of expression. So I've written it again on this slide. So this was the fixed length Liouville gravity partition function. And well, there exists a double scaling limit of this object that yields back the JT gravity partition function. And that is the object that I mentioned in one of my first slides. And the particular limit you should take to get to JT gravity is to take b to 0 while having the length of the boundary go to infinity in this specific way. So the length is proportional to the length in JT gravity, which is kept fixed as you take b to 0, divided by b to the 4th power. So this corresponds to a large boundary length limit. So this is double scaling limit in the end. And then if you look at the expression itself, so the energy that's here, so it's kappa times cosh to pi bs, it turns out that you can Taylor expand that and truncate it at the second term. And then it turns out that the integral here in this particular scaling limit is dominated by values for which s, the variable s, the integration variable, is b times k, where k is kept finite and b goes to 0. So that is the dominant contribution to that integral in this double scaling limit. So if you do that, so you substitute s equals b times k. So the first sinh you can Taylor expand it. The second sinh just becomes sinh to pi k. So that gives you this k times sinh to pi k you get in JT gravity. And then the exponential function, well, the 0th order term just gives you a constant that you multiply out or you renormalize your entire calculation by it. And then this piece just gives you e to the minus l jt times k squared, which is indeed the JT gravity disk partition function. So there is indeed a limit that you can take to go back from Liouville gravity to JT gravity, and it involves taking that parameter b to 0 in a clever way because, well, you have to take this double scaling. Okay, so that's one interesting comment. Another is that, so when we go back to the full Liouville gravity, I want to interpret, of course, this length as beta, the inverse temperature. And now I want to think about this more in a thermodynamic way. So I can write this canonical partition function as an integral over E instead of an integral over S. So the only thing I did here was, well, E is actually kappa cosh to pi bs. So now I call that E again. And that E integral ranges from kappa to infinity, e to the minus beta E, the Boltzmann factors, times an energy density of states, which is again just sinh of R cosh basically. Now, if you stare at that density of states, in the IR regime at low energies, and by low, I mean the energies is kappa, which is of course the bottom of the energy, plus something small, then you get back to the JT regime. So in the IR of this theory, you get back to the same density of states as JT gravity. But in the UV, your model is modified from JT gravity. So JT gravity had this Cardy scaling in the density of states. This thing actually has a power law scaling, as you can explicitly show by looking at that expression. Now it is interesting also to take a look at the thermodynamic limit or the saddle of this calculation of this canonical partition function. And if you do that, you find this relation between energy and temperature. Square root E squared minus kappa squared is 1 over B squared times the temperature. And again, you can investigate the IR and UV behavior of that saddle equation. In the IR, you get square root of the energy is proportional to the temperature, and that was precisely the JT black hole first law again. So again, in the IR, we make contact with things we already knew from JT gravity, but in the UV, at high energies, this theory is modified from JT gravity. And this saddle equation gets modified that the energy is proportional to the temperature. Now, if you want to interpret this thing as a holographic theory, you have this UV-IR connection. And because my model gets modified, or my density of states get modified at high energies, this means the near boundary region. So we expect a qualitative change of the boundary region of the bulk geometry. And in particular, we don't expect this thing to be asymptotically ADS anymore. And I will make comments about this near the end, or I'll try to interpret what it actually is near the end of my talk. But this is just some observation you can make just by thinking about this density of states and trying to interpret it as a holographic system. Okay, so that was everything that I wanted to say for the partition function. So now let's go on to the second object of my list, which is the bulk one-point function. So we have one bulk operator here. So just to remind you, this was the form of the bulk operator. And we transform that to the fixed length basis. So we do the exact same strategy as before. So again, if you do the calculation, the only thing you need to do is a contour deformation procedure. So it's a very similar calculation to do. So I skip the details here. And in the end, what you find is, again, an integral over S, the same kind of exponential function with the same kind of energy variable. And then instead of sinh times sinh, you get cosine 4 pi ps, where that number p is related to the alpha that was labeling the Liouville vertex operator as alpha equals q over 2 plus ip. So that's the relation between that number that's here and the number that's defining my bulk operator. Now, just because I will need it in the next few slides, you can explicitly do that integral, and you basically get a modified Bessel function of the second kind, where its index is basically labeling the operator, the bulk operator, and its argument is the total boundary length here. So that will be important for the next few slides. Now, this amplitude has a JT limit, as you would expect, and the JT limit is this single trumpet amplitude that I mentioned before. So this ZJT beta of B, or this defect partition function, that was used in the Schenker-Stanford procedures to get to higher genus, or to get to multi-boundary higher genus amplitudes. And there's a relation between that bulk operator label P and the geodesic distance parameter in JT gravity in this specific way. So because we already get from this bulk one-point function, we get this single trumpet amplitude, this suggests that we can actually understand within this Liouville gravity this entire same construction as Schenker and Stanford did, but instead of having this single trumpet partition functions, we have these bulk one-point functions in Liouville gravity being glued together. So that is something we will try to investigate in the next few slides. So let's think a bit about multi-boundary amplitudes. So the simplest one is the two-boundary amplitude that I want to compute in Liouville gravity. So I've drawn it here. So this is the annulus diagram, or the Euclidean wormhole, as we're supposed to call it now. So I want to calculate this thing in Liouville gravity. So I have two of these boundaries, so two of these brane boundaries, and I label them by S1 and S2 for the Liouville sector. So again, the S labels are related to the FCZT brane labels by this Koch transform. And I take the identity branes for the matter sector. Now, this calculation is actually, well, almost a textbook calculation you can do in string theory, and it was done by Martinek almost 20 years ago. And you can write that calculation in string theory as an integral over the cylinder worldsheet modulus. So this tau is along the imaginary direction, and it's just the single real modulus of the cylinder. And you integrate the product of the three partition functions, the Liouville piece, the matter piece, and the ghost piece on this cylinder's geometry between boundary states. Now, what Martinek did in his paper is he showed that if you take this object and you transform it to the fixed length basis that I showed you before, then this is explicitly calculable for several different choices for the matter sector. Now, because I will be interested in generalizing this calculation to more than two boundaries, I will specify it to the 2, p minimal string as the matter sector. And in that case, this is the answer you get if you follow basically Martinek's calculations. And this is a very suggestive answer. So what we get for two boundaries of lengths L1 and L2 is we get an amplitude that you can write as the integral of some parameter lambda with some measure lambda times tanh pi lambda, and then the product of two Bessel Ks, for which this index is lambda itself, and the argument is the length L1 and L2. So you can read this thing as two of these bulk one-point functions. So if you remember, these were precisely given by these kinds of Bessel Ks. So two bulk one-point functions where the lambda label here that I integrate over is related to that label characterizing the bulk operator insertion. And they're glued together by integrating over lambda with this specific measure. So the picture we have is that we can write this full amplitude in terms of this. So you can view this as two bulk 1-point functions that are being glued together with this specific lambda times tanh pi lambda measure. And you can explicitly evaluate that integral, and that is something that Martinek has done. And you find this thing, which is of course the universal result for a random matrix pair correlator. And this was some additional indirect evidence, 20 years ago, that this minimal string was indeed related, or given by a matrix integral.
Thomas?
Yes.
Can I ask you a question?
Yes, sure.
So in the JT gravity case, we can understand the measure that appears when doing the two trumpets, as you said, right, as the modulo.
Yes, yes.
In this case, is there some way of thinking about it in a similar way?
We don't know about it. That's actually, yeah, we don't have a geometric interpretation of getting that. That would be interesting. We think, well, I will give arguments as well that all this construction of Liouville gravity is related to a Q deformation or a quantum deformation. So what we actually want to know is how, purely from a mathematical and geometrical perspective, how these Weil-Peterson volumes and this entire construction gets related or gets generalized into quantum Riemann surfaces instead of the usual Riemann surfaces. But that is a pure math problem that we do not solve here. So I will only write things in a very suggestive way. But I agree that that's definitely something that would be interesting to understand. Yeah, I agree with that.
Okay, thank you.
Okay, so that was everything for the two boundary amplitude. Now higher loop amplitudes or more than two boundary amplitudes at genus 0 are calculable through matrix model techniques. So let me briefly sketch how that works. So this is part of a set of techniques that has been developed a long time ago and has been studied very recently by Clifford. So given a genus 0 disk density of states rho 0 of E, one can relate it to the heat capacity U of X by this integral transform. And there's this f of u here, which is related to the derivative of the heat capacity with respect to X. Now, in this case, we have the very explicit genus 0 density of states. So it was a sinh of R cosh. So we plug that in here, and we find an equation that gives you u of X. And that one is written here. So it's an implicit equation defining u of X. So X is on the right-hand side, and u is hidden on the left side. It's here, and it's hidden in the argument of this hypergeometric function. So ujt is just a scaled, shifted version of u, but that doesn't really matter. The important point is that we have an implicit equation giving u of X. So we start out with the known rho 0 of E. We get this auxiliary object u of X implicitly defined here. And then there is an interesting formula from the early 90s from Moore, Seiberg, and Staudacher, which says that if you know that heat capacity at genus 0, then you can compute the generic multi-loop amplitude by just evaluating this function. So it just involves taking n-3, in this case, derivatives with respect to X of some object that is a function of u of X and all of the lengths of the n loops that we have. And then in the end, evaluate it at u equals 1. So if you have an explicit knowledge of u of X, you can just evaluate that and get to the multi-loop amplitudes. And we have done that in the paper, but I won't give you the answers for that. Instead, I will focus on trying to write or rewrite this construction in parallel to the Schenker-Stanford construction of these Weil-Peterson volumes that are being glued together to these bulk 1-point functions or single trumpet partition functions. So to do that, I write this amplitude, this genus 0 multi-loop amplitude, in a second way, in a suggestive way. So I write it as a product of n integrals d lambda I goes from 1 to n, with the same lambda times tanh measure that we had for the 2-point function, so for the two boundary amplitude. I have this Bessel K function here, and then I have this quantity V0 n of lambda. Now, I can always write this expression to define what the quantity V0 n of lambda is, because this integral here is actually an invertible integral transform. It's called the Kontorovich-Lebedev transform. So I use the second way of writing it just to define this quantity here. And of course, this is a very suggestive way of trying to write things down, because this is now a rewriting in terms of glued bulk 1-point functions, which are basically these modified Bessel functions that are here. where their parameter is related to that lambda label again in the same way that we found for the two-loop amplitude or the two-boundary amplitude. And this V0 and lambda that I define using this is some deformed genus 0 Weil-Petersen volume, or at least I will interpret it like this. Now you can get a very explicit formula for that object precisely because this integral transform is invertible. So you just invert it back into the first equation, simplify it a bit, and then you get a very explicit formula for this object here. So I've written it here. So it's again, well, you still have the same structure. You have these n-3 derivatives in terms of something constructed of u of x. These p here are Legendre polynomials. And this is a very explicit formula. Of course, we still know this u of x only implicitly, but we can get any derivative of that u of x by using this Lagrange inversion theorem. Well, you can get a very explicit formula from that. And you can also take the classical limit of this. So remember, taking b to 0 was like a JT gravity limit. So if you take limit b to 0, we expect to make contact with the usual hyperbolic geometry or the Sachenker-Stanford construction. And taking the b to 0 limit of this thing gives you an explicit formula for the genus 0 Weil-Petersen volumes. And this generalizes a formula that Zograf wrote down in 1998 to finite size boundaries. So there's a slight mathematical generalization and an explicit formula of the genus 0 Weil-Petersen volumes that you can derive from just exploiting this matrix model description here. Okay, so that was all genus 0. Now, of course, as is well known in matrix models, higher genus corrections can be obtained through these topological recursion relations of Hénard and Orantin. And we have used that to provide a generic proof that, in our case, this VGN of lambda is also a multivariate polynomial in the lambda I squared, just like the usual Weil-Petersen volumes are multivariate polynomials in the BI squared. So to summarize this, the generic multi-loop amplitude at an arbitrary fixed genus G can be written in this very suggestive way. So n integrals over these lambda. So these lambda times pi lambda is the gluing measure in this case. A generalization of the Weil-Petersen volumes, which is again a polynomial on these lambda parameters, and then glued together with these bulk one-point functions. So we can draw this graphically just in exactly the same way as you draw it in ordinary JT gravity as a Sachenker-Stanford prescription. You have these bulk one-point functions here, and they're being glued together to some compact higher genus surface here, for which, well, the amplitude or the contribution to the amplitude is just these generalized Weil-Petersen volumes. And we have checked, so not just for these Weil-Petersen volumes only, but for the entire amplitude, that we can take a consistent JT limit of this to fully get back the Sachenker-Stanford procedure in ordinary JT gravity. And in particular, this gluing measure that has this hyperbolic tangent here, because if you follow the details and see how you should precisely take the JT limit of this construction, you should have this lambda here, which is of course, which just becomes the geodesic distance parameter in ordinary hyperbolic geometry. You should have it scale like that, but divide by b squared, where b goes to 0. So this lambda that I defined here is actually going to infinity as b is going to 0, which means that this tanh is going to 1, and I just get db times b, which is just the gluing measure that we understand for hyperbolic geometry. So we do get indeed the full Sachenker-Stanford construction back from this. But we have generalized this well, we have a one parameter generalization of this parameterized by that number b. And I want to think of this as a Q-deformed version of hyperbolic geometry. And near the end, I will try to make the statement exact, not necessarily for these multi-boundary amplitudes, but for the disk amplitudes. I will try to argue that you can really think of Liouville gravity as a quantum deformed version of JT gravity. So I'll mention that near the end. Okay, so the next one on our list is the boundary two-point function. So that's the third amplitude that I want to discuss. So I have drawn that here. I have two boundary operators, roughly corresponding to that kind of operator, and they are separated by fixed length segments of lengths L1 and L2. So the strategy is again the same. We start with the Liouville boundary two-point function, which is again known in the literature, and we transform that to the fixed length basis. In this case, we have two fixed length segments, so we need to do a double Fourier transform of that amplitude. Now I will skip the details of this calculation. You can find it in the papers. And this is the answer you find. So it has two integrals over S1 and S2, rho S1, rho S2, where both of these are the sinh times sinh density of states we had in the partition function. You get these e to the minus, well, energy label times L1 and the same one for L2. So these are Hamiltonian propagation factors, if you want, or Boltzmann factors. And then this thing, which is again like a vertex function, a product of SB functions. So SB functions are special functions, they're double sign functions. And I've also defined this beta m here. Beta m is related to to beta in this way. So beta m is b minus beta, and it's interpretable as a matter label. So beta was the label for the Liouville vertex operator. Beta m is the associated label for the matter operator. And well, if you describe your matter as time like Liouville, this is literally also a Liouville label. So the structure you get is very, very analogous to the structure we had in JT gravity. So I will make, I will take the limit on the next slide. So this is of course no coincidence that the structure is the same. Just a small comment here. So throughout this talk, I have not said anything actually about the matter and ghost pieces to all of these amplitudes. That is because all of the interesting part of any amplitude is always in the Liouville piece, because I'm transforming it to the fixed length basis, and that only acts on the Liouville piece because that's where the mu b is, that's where the FCCT parameter is. But in this case, there is something interesting happening for the matter sector, because the boundary 2-point function, this is a CFT. So that one, well, it's some constant that I transformed here in this calculation. Of course, divided by the separation between these 2 points to the 2 times conformal weights, as usual in CFT. So that is just the worldsheet coordinate dependence of the Liouville 2-point function, or Liouville boundary 2-point function. But the matter and ghost sectors also have worldsheet coordinate dependence, and the sum of all of these, which means that the conformal weights get added together, that won't give 0. So the entire role of these 2 sectors is just to cancel out the worldsheet coordinate dependence. The answer we have in the end, it does depend on these length parameters, but these lengths are not worldsheet parameters. They are defined in the Liouville metric, not on the worldsheet. So that is an important distinction to make in this calculation. We've also seen it, for instance, for the 2 loop amplitude. We have integrated out, in that case, the worldsheet modulus, the tau, the worldsheet modulus of the cylinder worldsheet. So all of these worldsheet coordinates, they are sort of integrated out, or they disappear. They don't play a role. We get something that is fully defined in terms of the physical Liouville metric instead. Okay, so now let's try to analyze, well, first the JT limit, and then try to do some physics with this thing. So this is again the answer we had on the previous slide. Of course, there is a JT limit, which is again to take B to go to 0 and beta m, this matter label, to scale in a particular way. There is a well-known, or Taylor formula for SB of Bx as you take B to 0, and that is the thing we need, and it's just the gamma function. And that means that this thing is entirely going into these gamma functions, and this is precisely the JT gravity boundary 2-point function. So again, there is a nice limit to go back to JT gravity. Now, I want to, instead of being in JT gravity, of course, I want to take a look again at this full Liouville gravity boundary 2-point function. And now I want to think a bit about the real-time version of this. So I will reinterpret L1 here as I times t, where t is a real time, and L2 as beta minus I times t. So this is the real-time thermal 2-point function that I want to think a bit about. And staring at that expression and using some formulas for the asymptotics of these double sign functions, you can distill these properties. So first, at early times, that means when this t goes to 0, when the time separation between the 2 points measured in the Liouville metric, but well, Wick rotated to real time, when that t goes to 0, you get a pole, which goes as 1 over t to some positive number, which means, well, you have a UV divergence if these 2 operators come together. And then at late times, you find a power law decay, which goes as 1 over t to the 3rd power. And if you know about these late time behavior of holographic correlators, then this would correspond to the slope region. So you have this slope, ramp, and plateau. This power law decay you find here corresponds to the slope region of that correlator. And that is precisely the same late time behavior that JT gravity has, and late time corresponds to small energies. And we already saw in the partition function that at low energies, this entire theory goes back to JT gravity. So it's no coincidence that we find precisely the same late time behavior as JT gravity. Now, if you would try to go to very late times, far beyond where this slope is, you might expect to be, well, very far in this JT regime. So we expect the same explanation for the ramp and the plateau contributions to the boundary 2-point function than the one in JT gravity. And these come from higher genus effects. Well, to emphasize, I have only analyzed the disk amplitude up to this point. And from the disk, you can get the slope. But because you go to the JT regime at late times, you do expect that you get the same kind of explanation for even later times, the ramp and the plateau, to come from higher genus corrections to these kinds of boundary 2-point functions. But of course, we cannot really compute these directly, especially in the worldsheet language. So let me first briefly explain or review a little bit about how these ramp and plateau contributions appear from higher genus effects, or more generically, how higher genus effects for the boundary 2-point function actually work. So how do higher genus corrections work for the 2-point function? So there's a general expectation, which was worked out by Phil Saad last year, that the higher genus corrections correct only the density of states factor in the correlation function, at least in JT gravity. So this was analyzed in JT gravity, and that is, well, for the purpose of this slide, I will just go back to the JT gravity limit. So that means if you think about the boundary 2-point function, so it had two integrals in it that I called K1 and K2, or basically E1 and E2, and it had two densities of states, which are just sinh density of states. Now, the general expectation is then that higher genus corrections are encoded just by replacing this product of genus 0 density of states by the full random matrix theory pair density correlator for the specific ensemble that is dual to JT gravity. So for arguments for this, you can take a look at his paper. Now, this, or quite generically, this pair density correlator can be written as something that is the product of two single densities plus a connected piece. And this has a geometric interpretation. So what I've drawn here is the JT disk where two boundary operators are inserted at these endpoints of these blue lines. And I have connected them by a bulk line, as you can see here. And then I have added higher topological or higher genus corrections to these. And you can see that the first two diagrams, this one and this one, where the second one, of course, represents an entire class of diagrams. This represents the disk topology and the disconnected higher topology. And I mean disconnected, that the left-hand side of this line and the right-hand side of this line are not connected through some bridge, let's say. And this corresponds to in random matrix language, to this first piece, the row E1, row E2. Whereas the last diagram here, it represents the connected higher topology. So this corresponds to this connected piece. And it's precisely this piece that leads, well, the perturbative piece at least, leads to the ramp contribution, and then non-perturbative corrections to this structure give rise to this plateau. So we have investigated that, and this was further studied more systematically again in Phil Saad's paper. So this is the generic expectation how this ramp and plateau appears, but applied to the boundary 2-point function. While the usual discussions that you find, for instance, in the Saad-Schenker-Stanford paper, they apply this to the spectral form factor. Okay. So what I will investigate next is the boundary 2-point function and the higher genus corrections, but in a special case, and this time for the minimal string. So this is a special case of the last couple of slides, where I specify my matter theory further to be this minimal model. So a brief reminder, the minimal string has, its only primaries arise from degenerate Virasoro representations, which means that beta M label, that matter label, is fixed to be in this specific range, to follow a degenerate Virasoro representation. And this, you have this N label and M label, they go in this range, and for the Q, P minimal model. And this defines a finite discrete set of possibilities of these boundary operators. Now, if you further specify to the 2, P minimal string, this formula simplifies a bit, and we just have this kind of structure. So beta m is just minus b over 2 times some integer in some range. Now, if you specify to these values of beta m, and if you remember roughly what the structure looked like for the boundary 2-point function, so it had these vertex functions. So let me briefly go back to them. So it had these things, sb of 2 beta m in the denominator. And for these specific values of beta m, this sb function has a pole there. And if this sb function has a pole in the denominator, that means that the entire amplitude is 0, unless it gets compensated by something happening in this numerator. And that can happen, but that requires a relation between the S1 and S2 labels, which causes a restriction of your integral. And that is indeed what happens. So that amplitude is 0 unless the numerator is also 0, which gives you a one-dimensional subspace of the integral. And if you do that, simplification, and you do the calculation, then this is what you find. So it looks a bit more, it looks annoying with this sum and this product, but it actually has a nice origin. And I will explain that on the next slide. But the important part here is that this only has a single integral left. So one of the integrals is gone. There's only a one-dimensional subspace of the integral. So this is a very specific subclass of boundary correlators for which the structure is actually quite different from the generic ones that we talked about up to now. Now, you can again take a JT limit of this, and this matches with an independent calculation you can directly do in JT gravity, where you take the weight of the boundary operator in JT gravity to be a negative half integer. And as I mentioned, this has a simplified structure because there's only one integral here. And I have used that to investigate the expansion in the Newton's constant of the 2-point function in JT gravity itself. So you can find the details in my paper. This is not important for the purposes of this talk. The reason that I mentioned this is because the calculation that leads to this actually is very suggestive on how to think about higher genus corrections to this boundary 2-point function. And that is what I want to mention now. So the above suggests a natural generalization to higher genus. And to see that, I have to actually show you a bit more of the details that go into this small calculation. So, well, on a technical level, the Liouville 2-point function, which is the main ingredient to go to these Liouville gravity fixed length amplitudes, for this specific operator insertion, so for this degenerate Virasoro operator insertion, it looks like that, where this b plus b j over 2, that is a specific choice of the degenerate matter insertion. And it turns out that in this very specific case, these complicated special functions, they actually just reduce to elementary functions like this. So there's a simple formula that this thing is related to this thing. And then you can transform to the fixed length basis again, as we're always doing, by doing the same sort of contour deformation. But in this case, the contour deformation works a bit different, because one of the contour deformations, so you have two contour deformations to do for the two Fourier transforms, and one of them is only picking up the poles of this denominator. And then the second one is giving you a discontinuity across the branch cut. And that explains why you only have one integral left. One of them is actually reduced to a pole contribution. That is why there's a sum here. This is just a sum of the residues of that second integral, and that's it. And you can see that product here, that strange product. Well, you can see it's just this product, but evaluated on the poles, and that's it. So this is a way to get to that result, and one way of proving it. The reason that I have sketched this calculation here is because there's a very suggestive, there's very suggestive ingredients here. You see an explicit appearance of the genus 0 resolvent, this cosh 2 pi over b s1. So if I use a random matrix language, this would be the genus 0, or the first contribution, let's say, in the genus expansion to the resolvent in the matrix language. And then the spectral density, rho of s, well, I've always done that, but you get that just by taking the discontinuity of that thing. And the discontinuity of the resolvent is just, well, the spectral density in matrix model language. So this immediately suggests a strategy on how to get to, or how to get a proposal at least, or to go beyond genus 0. The only thing we need to do here is just replace where the genus 0 resolvent is, just replace it by the generic resolvent, or the all genus result. And then, well, then the only thing that gets changed in this calculation is that rho of s, that density, just gets replaced by the exact answer from random matrix theory. And in particular, there is no paired density correlator contribution. So I mentioned 2 slides ago, that generically, the generic boundary 2-point function, you get row 0 E1, row 0 E2, and they get replaced by row E1 comma E2, the pair density correlator in the random matrix ensemble. And that one gives you that, that one gave you the disconnected contributions plus the connected contributions and so on. But in this case, you can see, because there's only one row S, and well, if you believe that this argument that I gave you here, there's no pair density correlator here. There's just a single density correlator in the random matrix language. So this suggests that this thing can be viewed just as the disk plus genus 1 plus genus 2, very much like the higher genus contributions to the partition function itself. So these kinds of correlators, or at least that's what I'm suggesting here, the higher genus corrections are way more similar to the ones in the partition functions than the ones for generic operators. And by the way, also, if you don't insert an operator in this language, that one actually also corresponds to the lowest of these operators. So the partition function itself, when there's only the identity operator is included within this discrete set of minimal string operators. So that is also why I believe this is natural. Now, of course, ultimately, this is a proposal, but to really check that, one would just have to actually compute these things, for instance, in the worldsheet language, and to see whether this is true or not. But of course, we are not capable of doing that. So at the moment, this is just a proposal, but it sort of blends in together all of these different approaches to the topic. So these older techniques combined with the recent perspective by Sachenker and Stanford and so on. And I believe this is a quite natural proposal in this language. Okay, so very briefly, I think I'm running out of time, or how much time do I have left?
I think we started at 10:05 or so, so we can have 5 or maybe 10 minutes more if you need to.
Okay. Okay, so I'll go a bit quicker through these slides. So as I mentioned, we also analyzed other amplitudes, the boundary 3-point function and the bulk boundary 2-point function, and you can analyze them. They have nice JT limits, which I have drawn here, and you can write the analytic amplitude and interpret everything in terms of JT gravity. But let me skip through the details of this slide and go through the last portion of my talk, which will be to give 2 different perspectives on these fixed length calculations. The first is a group theoretic interpretation. Now, JT gravity has a group theory interpretation in terms of a structure related to SL2R, and I will propose a related structure for Liouville gravity. And let me focus on the example of the boundary 2-point function. So I've written out the boundary 2-point function again in JT gravity here. Now, it turns out that this measure, this k times sinh, and the energies, the k squared, they match with the Plancherel measure and the Casimir of a continuous series of irreducible representations of SL2R, or well, I should say some modification of SL2R. You can find the details in this paper, so I won't go into the details here. And then this last structure, what I call the vertex function, also has a group theoretic origin. It is a 3J symbol associated to suitable representations of SL2R, where I take 2 continuous representations associated to the state, so those are the K1 and K2, and 1 discrete lowest weight irreducible representation associated to the operator H. And then there is a generic formula that gives you 3J symbols, or better, the product of 2 3J symbols, as a group integral of the product of 3 group representation matrices. So this is a very well-known formula for compact groups. So this Rj Mn of G, these are group representation matrices. You can write this as in a bracket notation like that. And for instance, if you apply that just to SU2, you get these Wigner D functions. I don't have SU2 in this case. I have some modification of a constrained version of SL2R. So there's lots of fine print here that I will skip. But let me just sketch on how it works. So applied to our specific case, you also get an integral over some variable x times the product of 3 group representation matrices. And in this case, if you work out the representation theory for the specific case of SL2R and the specific representations we want, you find that these group representation matrices for the continuous representations just are Bessel K functions. And the discrete ones is an exponential function. So you get two of these Bessel K's, one exponential function, you do that integral, and you get this structure, which is indeed just the one we had here. So there is a group theoretic way of even explaining these vertex functions. That's what I wanted to say here. And you can just read them basically as the product of two 3J symbols. Now, the most important ingredient in this construction is this RK00X, which is a constrained matrix element in the continuous representation. This is this Bessel K function. In the math literature, these things are called Whittaker functions. So this is the story. Well, this is the very, very short version of the story on how JT gravity has a group theoretic interpretation. This is, of course, no coincidence because JT gravity itself can be written in its first order formulation as an SL2R BF theory. So there is a gauge theoretic way of writing JT gravity associated to SL2R, and the amplitude then is automatically structured using objects from group theory of SL2R. Now, what I want to briefly show is that there is a very analogous structure for Liouville gravity. So the claim would be that Liouville gravity amplitudes arise from a constrained version of what is called the modular double of the Q-deformed version of SL2R. And by that parameter Q, I mean e to the pi IB squared, and this B is the Liouville B that we had before. So without explaining what these things are, I just want to mention that this strange structure has a set of continuous irreducible representations labeled by a parameter S, for which the Casimir is cosh to pi bs, and the Plancherel measure is basically sinh times sinh, which is the same measure that we encountered lots of times already in our calculations. So let me again take the example of the boundary 2-point function in the Liouville gravity. So this is the answer that we derived. And again, the measure and the energies, they match with the Plancherel measure and Casimir operator. So I've written them here. So the main question is whether that object can be viewed as the 3J symbol, well, 3J symbol squared of a group integral of the product of three group representation matrices. And the answer is yes. So the Whittaker function for this Q-deformed SL2R has been computed in the math literature, and it's this complicated expression. So it was just this Bessel K function for SL2R, and that one gets replaced by this thing, which has this double sign function in it as well. So now if you take two of these things and one discrete insertion, which is just that exponential function, you can actually do that integral using some mathematical tricks, because of course this doesn't look easy when you look at it, but you can actually do those integrals. And indeed, you get that thing we have here. So there is an extremely analogous interpretation of Liouville gravity for all of the objects that appear in these amplitudes, but this time in terms of the quantum deformation of the SL2R structure. And then very, very briefly, this is still work in progress, but we are trying to analyze this thing for Liouville supergravity. And we have a proposal for this group theoretic structure for this Whittaker function there, which was not previously known in the math literature, but we have some checks that this seems to be the correct object. In particular, that 3J symbol calculation can again be done, and it gives you the correct object for Liouville supergravity. But okay, I'll skip this largely. Then I come to the final piece of my talk, which is to give you a dilettante gravity perspective of Liouville gravity.
Quick question before you,
yes.
Sorry to interrupt. I think a lot of our audience might not know what a quantum group is, and I guess in some ways you've kind of defined it in your previous slide by in terms of having some sort of deformation of the algebra by this parameter.
Yes.
And so what you're seeing is in the various formula you wrote in that previous slide, you're essentially seeing the formula you wrote down before, but now with those exponential factors. And so you're saying in that sense, it's a quantum group deformation. Am I getting that right? Or is there something deeper going on?
I'm sorry, what do you mean by these exponential factors?
Well, so I'm trying to trace back the appearance of what you're calling Q, which is e to the I.
So Q, yes. And that is the Liouville B. And if you take B to 0 to go to the non-deformed, you get Q equals 1. That is the undeformed case again.
Right. And so you're saying sort of structurally then all the amplitudes you write down have in the right place these factors of Q that then correspond.
But Q is encoded in the B's that are everywhere hidden in these formulas.
Oh, I
so
see.
This B is related to the Q.
Yeah. So it's more than just the factors you wrote. So you're saying there's a lot you haven't shown us here, where you're defining the quantum the quantum group extension of SL2R.
Yes. So this was studied by many people. Yeah, this was studied by and Teschner mostly, and of course the mathematics literature. So I'm just the only thing that I have told you, and without any sort of arguments here, is that there exists a set of irreducible representations with these properties, and that this structure precisely matches to all of the ingredients we have here. I have not explained why this is so or where this comes from.
Right.
This is.
I guess you also haven't told us what a quantum group is. For pedagogy.
It's a deformation of a classical group, basically. And for the purposes of my talk, I don't really need to sort of delve into those details, I think. Yeah. I just want to mention that there is a mathematical structure that generalizes ordinary groups, and that mathematical structure explains all of the ingredients in the Liouville gravity calculation.
Yeah. I always going back to years ago when people were doing a lot with quantum groups. I just know for our younger audience, shall we say, that it can often be confusing because it's not quantum in the sense you might think, and so I assume that's
yes, that's right. That's right.
Yeah,
it's quantum the way mathematicians define it as a deformation of some structure, and
yeah.
Anyway,
thanks.
I have a question about some related things. So this quantum group interpretation is nice, and I was wondering whether this. So in your previous discussion, you have defined these deformations of the Weil-Petersen volume.
Yes.
And it was hard to understand geometrically or what's exactly what they were doing.
Yes.
Maybe this perspective is useful in that regard.
Yes. But I agree, that would be interesting, but we don't know how that works. We don't know how to really interpret those measures in terms of Q deformation of some sort. So we only understand these measures here, the exponential factors as Casimir operator, and then these objects. We don't understand these Weil-Petersen or these generalization of these Weil-Petersen volumes, but morally they should be roughly the same, right? That is sort of the conclusion we seem to be getting. It seems like we're deforming everything from JT gravity, and when we're restricting to disk amplitudes, we're deforming them in a mathematically precise sense using this quantum group structure. So then it seems very suggestive to think about these Weil-Petersen volumes as being the analogous deformation of some sort, but I don't know. It would be interesting to understand that better. Definitely, I definitely agree with that.
Yeah,
but I also fear that it might be a very hard mathematical problem that would be purely mathematical as well. So
yes, I'm thinking that maybe it's too naive to expect the deformation to have such a geometrical and intuitive picture the original Weil-Petersen volumes have.
So definitely words like geodesic distance and so on, they get strange, right? I mean,
yes, and in this case, it's a fully quantum theory that has much more dynamics than the original JT gravity. Maybe it's naive to expect to have, I don't know, a metric or I don't know, something like that surviving the quantum limits. So.
Yes. I agree with that. So it's, intuitively it's harder to think about these things, but morally I think we should think about these Weil-Petersen volumes on the same footing as I explained here in this slide.
Yeah,
that is all. I don't have a technical thing to say.
One more question on that point, and don't worry too much about the time. You can count this in the discussion.
I'm almost done in any case.
So it's been a long time since I've thought about quantum groups, but I seem to remember that there was a very nice connection to certain kinds of additional integrable structures that you have.
Yes.
do they play some role here? Somehow there's some sort of enhanced integrable structure in the Liouville theory, which somehow goes away in the quote unquote classical limit and becomes JT.
I don't know. That would be very interesting. And well, I have been reading a bit about integrability in relation with this, but I haven't understood it sufficiently in this context. So yeah, it would be very interesting.
Yeah.
Also, by the way, these minimal string boundary operators or these correlation functions you get from that, I do believe that you can think of those as some sort of integrable subclass of operators, whereas the generic ones would be, well, the generic ones are well, they give chaotic physics and so on. And this is this discussion people always have on how integrability and chaos can coexist, let's say. But I think in this case, most of the operators give you chaotic physics in the end, or give you, well, if you do the 4-point function, you get this Lyapunov growth and so on. While this restricted set of operators that the minimal string has, they would give you instead an integrable sector, I believe. But yeah.
That's a different integrable from the Q deformation integrable.
Yes.
Yeah.
Although that is for the full Liouville gravity, so that is, from this perspective, the Q deformed version of JT.
In the same limit,
again.
yeah. Okay, I should let you go on. It's a very tantalizing picture you've uncovered, so it's kind of
Thanks.
Kind of nice. Okay, carry on.
So in the last part, I want to briefly mention some things about how to think of the Liouville gravity as a dilaton gravity with a specific dilaton potential, which will be hyperbolic sign potential. So I will first sketch an argument at the level of the action. So for that, I need to describe my matter sector now in a specific way as a time-like Liouville sector. So I have a usual Liouville sector and my matter sector described as time-like Liouville. And then I do a field redefinition in that action. So the Liouville field gets roughly rewritten as rho minus big phi, and then the chi field as rho plus big phi. Big phi will be the dilaton field in the dilaton gravity description, and rho will be related to the conformal factor of the metric in the dilaton gravity theory. So just redefining the sum of these two Liouville theories in this way, you can rewrite your action in this way. And then the first term, the d phi d rho here, well, if I write a metric like this, ds squared is e to the 2 rho dz bar. So this defines what I mean by rho in terms of a geometry. Then you can see that that first term is just giving you square root g r times phi, which is the generic form of how dilaton gravity, how the dilaton couples to the Ricci scalar. And then the second term, e to the 2 rho here is square root g again. So this is the integral square root g of some function of phi only. And this would be the dilaton potential. So doing that field redefinition, this sum of Liouville theories gets rewritten in terms of a dilaton gravity theory with a specific form of the dilaton potential. Now, if I restrict to the case where this bulk cosmological constant of matter and Liouville have the opposite sign, I precisely find the sinh dilaton potential. And there's a b here, so that if I take the small b limit, I Taylor expand the sinh and I get a dilaton potential linear in phi, which is JT gravity, as shown for the amplitudes above, that this limit is indeed giving you JT gravity. So this is a suggestive argument that at the level of the action, you can rewrite Liouville gravity in terms of dilaton gravity with the sinh potential, and then the sinh goes back to phi itself if you take the JT limit. Now, the argument is not understood sufficiently, or at least we don't understand it sufficiently. We are still confused by how this works with operator insertions. So I view this more as a guideline than at the moment than as a rigorous proof. So to argue that indeed Liouville gravity can be written as a dilaton gravity with the sinh potential, I will next present two pieces of circumstantial evidence for this. So very briefly. So the first piece is on the first piece of evidence is on classical gravity. So a generic dilaton gravity can be written like that. Now, in two-dimensional dilaton gravity, you can write down the generic classical solution of this model like this. So ds squared is minus a of r dt squared plus dr squared over a of r. Phi of r equals r. And then a of r is this integral of the dilaton potential. So just using diffeomorphism or coordinate transformations, you can write down this generic form of a solution to this gravity model. And this describes the black hole geometry with the horizon at r equals rh when this a of r is 0. Now, you can also write down, quite generically again, the energy as a function of Hawking temperature of the black hole solution as a function of this arbitrary dilaton potential, and it's written by this equation. And then, of course, if I now choose my dilaton potential to be a hyperbolic sine, I get an energy as a function of Hawking temperature relation of the classical solution of that. And if I choose it like this, then I get this relation. Square root e squared minus kappa squared equals Hawking temperature divided by b squared. And this precisely matches with this first law I have derived in the thermodynamic limit from the disk partition function at fixed length. So a cinch dilaton potential precisely gives you the correct semi-classical black hole first law. So that is, I think, an interesting piece of evidence that this is on the right track, because we have already derived this first law before. We were just looking for a black hole solution that has this property. And if I have a cinch dilaton potential, then I automatically get it. And then, okay, so, well, if now you have this black hole, now deep inside the bulk for the radial coordinate, very less than 1 over b squared, very much less than 1 over b squared, we get back the JT black hole. But if you go closer to the boundary, you get deviations from that. So this is precisely as we predicted, this UV region, the near boundary region, that one gets modified from JT gravity. And in fact, near the boundary, things get very weird. So you can compute, for instance, the Ricci scalar, and it blows up at the boundary. So it seems like there is some sort of curvature singularity at the boundary. So we definitely need to better understand the near boundary asymptotics for this cinch dilaton gravity theory. But I do find this argument quite suggestive here. So now let me present a second piece of evidence for the cinch gravity model. And that is that we can write a generic 2D dilaton gravity theory with the potential via phi in its first order formulation as what is called a Poisson sigma model. So this is some gauge theory that we have here. So I won't really explain what these objects are. So this, well, only this P of x that's called this Poisson tensor, and it's fully determined for the specific case of 2D dilaton gravity in terms of dilaton potential V. Now, the only thing that I need from this structure is that this thing has a symmetry algebra that is a nonlinear gauge algebra, a nonlinear generalization of a Lie algebra. And the nonlinearity comes from this arbitrary dilaton potential that is hidden in the commutation relations here. Now, of course, in particular cases, if phi of phi is 0, then this is an ordinary Lie algebra, and you get the 2D Poincaré algebra or flat space JT. If phi of phi is linear in phi, you get an ordinary Lie algebra again, and this is the SL2R algebra. But if v of phi is a cinch here, you precisely get the quantum deformation of SL2R. So what you see from this argument is that the cinch dilaton gravity immediately gives you this quantum group structure. But we already found that Liouville gravity leads to structure from this quantum group. So this is, again, indirect evidence that Liouville gravity and dilaton gravity with the cinch potential seems to be strongly related. Okay, so I will skip this and I will immediately go to my conclusions. So I have investigated fixed length amplitudes of Liouville gravity with the goal of extending our class of solvable 2D gravity models. And I've tried to phrase everything in the same language as ordinary JT gravity. And I've calculated several amplitudes, so I list them here. And I've also used matrix model techniques to shed further light on these calculations, and in particular to calculate multi-boundary amplitudes, and also to make a proposal for the higher genus corrections to the minimal string boundary correlator. Now, some of the lessons from this is that all of these amplitudes have a B to 0 limit where they match onto JT gravity amplitudes. The amplitudes display a quantum group structure, as I tried to explain, and they correspond, or they seem to correspond gravitationally to an exact quantum solution of a dilaton gravity model with a hyperbolic sign potential. Okay, so thank you.
Let's thank Thomas. It was a very nice talk. So now we have time for questions. If you have more questions, that would be good.
Sorry for going over time.
No, it's good. So I have a small question. You just sketched the connection between this dilaton theory with the cinch potential.
Yeah.
But your starting point, of course, is to take the matter sector as this time-like Liouville theory.
Yes, yes. So that seems like an assumption. Although I think it was last week. Yeah, last week there was this paper that precisely investigated how the minimal models are sort of encoded in time-like Liouville theory, and I think their strategy was to in time-like Liouville to do a periodic identification of the Liouville field itself. And apparently that makes contact to the minimal model. So it seems like they are sort of captured by time-like Liouville.
This was the paper by Daniel Capek and
Capek and yes, precisely.
Oh, I see. I didn't read. I have it in my list, but I haven't read it. I see.
And their goal was precisely to analyze this kind of argument for the minimal string and for on how it relates to dilaton gravity.
Oh, I see. So in some sense, it might be that simply just by taking the time-like Liouville, you have all the minimal models encoded in some way.
Yes, or at least they're closely related to it. It's not like it's a completely unrelated model. I think that's a conclusion, but
if you try to do the same thing for the simplest minimal model, I don't know, you take the easiest thing and you try doing some identification.
But for the argument near the end, I needed this Lagrangian description, of course. So I need to, at least that was for that argument, to relate it very explicitly, or to try to relate it explicitly to this Sinch dilaton gravity. That's why this time-like Liouville perspective on the minimal models seems very interesting, because now you have a simple Lagrangian formulation apparently. But I have to study their paper in more detail. So yeah.
So one of the things people often ask me when I talk about thinking about everything in terms of minimal models is, is how you go from things we already knew about minimal models to, on the JT side, you simply have this nearly ADS2 structure, and you have to work hard to see that on the minimal model side, as it were. So in a way, I think from your perspective, I guess you're saying, in a way, you're building the full ADS2 geometry by essentially improving the UV. And so I guess I think of it as an infinite set of minimal models that are all sort of coupled together in just the right way. And so what they're doing in some sense is they're conspiring to build the full ADS by everyone supplements the UV a little bit more, so you can kind of stretch out more until you build the whole ADS2 space. I think that's sort of,
that's a nice way of thinking about it. That we're sort of, because the UV structure geometrically is strange in full Liouville gravity, but taking the limit gives you something asymptotically ADS. And so any particular minimal model kind of fails, but somehow they collectively conspire to sort of hold the whole thing up. That's sort of how I think about it, and it's borne out by, I think, your nice picture of how you think about I agree.
amplitudes.
I agree with that picture. It seems like something very delicate to modify it in the UV like this, and I agree. It seems to be suggested here as well.
It's kind of nice, and it fits. And then of course it then fits with the picture immediately. Then you go, why is JT special? Well, it's just a particular recipe, and there should be other recipes. And these are things that Felipe and I have been thinking about. There's all of these nice deformations that you can write down, and you should be able to build them as well as different recipes for different minimal models. And it seems to work quite nicely.
But by deformations, do you mean these deformations studied by Witten and Maxfield and Turiac? Okay, I see.
We hope to have some nice results to present soon. So.
That would be interesting. I think this particular model, this Sinch model, does not fall into the class of deformations that they study.
Indeed.
Because they require that the asymptotics stays linear. You know, the dilaton should go linearly, the JT model, and it only modifies things in the middle. So they have this gas of defects, but somehow it doesn't modify the UV. And we were actually sort of playing around at some point with their formulas, and we didn't manage to find the Sinch model as a deformation of these models. So the formulas don't work. So it doesn't seem like you can modify it like that.
Yeah, it is one of the most amusing things that I think about those formulae, which is that you go, oh, these deformations, and you look for your favorite special case, right? That you understand very well, and it's not in there.
Yes.
Yeah.
Yes, but you might be tempted in the beginning, even though that the actual derivation uses a sum of damped exponentials in the dilaton field. Still, you might hope that it would hold for a generic function of the dilaton, but I don't think it does. It really
sure
needs to be damped.
Yeah, I'm sure there's more that can be done, but yeah, the initial picture is a little bit more restrictive, perhaps. Yeah. But anyway, probably.
Yeah, one of the things I also wanted to study or understand in that language is whether these boundary correlators can be computed. Including these deformations, but I got confused by that. So somehow I wanted that the only modification again would be just the spectral density.
I see,
and not these sort of interaction vertices or these vertex functions, as I call them.
Right.
I only wanted the modification in spectral density, but I find it hard to prove. So
right. So the guess would be that put in these modified spectral density functions into that same formula.
Yes.
Right.
It seems to be almost, it seems to be the case like that for a lot of calculations, that the only modification is always in the spectral density. That one gets modified all the time, but these vertex functions don't really get modified that much. Seemingly. I mean, it's the impression I get. Yeah. But of course, Liouville gravity does modify them. So there was these bunch of gamma functions for JT gravity, and they became these SB functions for Liouville gravity. But Liouville gravity is modifying the UV, so I'm not surprised that they are modified, because I tend to think of these vertex functions as coming purely from an interaction of the boundary with something that's being, that you shoot into the bulk. So it's a local interaction that happens at the boundary. So it only feels the UV, I think.
Yeah. I mean,
this is all speculation. So
yeah.
These calculations these correlations that we have in computing, there's no way of including a defect in them. This is to say, let's say you're looking at two boundary operators. Can you include a defect inside and do the computation, or that's not possible? By
defect, you mean an additional bulk operator?
No, I mean a defect in the same sense as these papers are doing, an actual defect in the space-time matrix.
Like a conical defect and so on.
Yes, exactly.
Okay, but those kinds of things, they can actually be found from the Liouville gravity from bulk one-point functions. So in this case, I have picked the bulk one-point function. So maybe I can go back to that slide. Yes. So I have picked this here. So this P alpha is Q over 2 plus IP. That is precisely the parametrization to have, these macroscopic tubes geometrically appearing here, or macroscopic operators, as Seiberg calls them in Liouville theory. But I don't have to pick this. I can pick alpha to be real instead. And that would correspond to a conical defect in the geometry that we have here. So these things also are encapsulated in these calculations. But you just don't need these to glue things together. If you want to glue, you need these continuous or these macroscopic tubes. But you can, the gas of defects is really this thing in the Liouville gravity language. So this is one defect, of course. You need
exactly. So if you want two defects, you need two insertions. If you want 20, you need 20. And in that case, I imagine the computation becomes contractible because you were talking about the ratios and so on.
Yeah, although some things can be computed. So I know that Joaquin Turiachi. He's thinking about this. So he has arguments on in particular how this string equation gets modified if there are defects in there, if there's this gas of defects in there. So in his paper with Henry Maxfield, they modify the string equation basically because of this gas of defects. And he has, as far as I know, he has the exact answer for the string equation deformed by this gas of defects for Liouville gravity.
Yes, I think I saw talking which he showed some preliminary results.
Yes. Yeah. So as far as I know, he has, or they have done this calculation.
Yeah, I wasn't thinking about the calculation from this perspective, as insertions of bulk operators, but yes, that's interesting.
Yeah.
I have another question, but I suspect I may be stealing Ashton's question, because he's been thinking about some of the BF formalism that you mentioned, and how extensive is the literature on some of the supersymmetric extensions
of JT gravity or of Liouville
to the BF formulation?
How JT supergravity relates to the BF formulation? Yeah. I don't think it has been worked out that much. We're actually trying to do that also at the moment.
Yeah, that's what it sounded like. So I was just wondering.
So I mentioned near the end that we were thinking about the group theoretic interpretation of Liouville of Liouville supergravity, but we're simultaneously working the things out for ordinary for the undeformed case, for JT supergravity. And that one is related to OSP 1/2 as a supergroup structure. And you can do the same thing. So we understand the analog of these steps for that case. So also this calculation of the analogous object here in terms of an integral of the product of three representation matrices. So we can do those integrals in those cases as well. But we haven't understood everything, but I don't think there is available literature on this yet.
Right.
Yeah. But,
so,
okay,
oh, sorry.
No, sure. Go ahead.
I was going to say, well, I mean, you don't have to answer this, but I know that you historically have preferred like the semi-group approach to, like when you did, you quantized JT for SL2R plus, right?
Yeah. So there's this universal cover. That's what I mean by modification of. And there are several proposals. So we have this what we call, this sub-semi group. So we have a plus here, and another group has a particular limit of the universal cover of SL2R, and they seem to get the same results.
Right.
So
it's a central extension.
At the moment, there are two proposals. So the proposal that we made for this sub-semi group, and this has confused us a lot and a long time. The motivation for that is in part precisely this Q deformation story, because Liouville theory on its own is related also to this modular double of UQ-SL2R. And this word modular double is important here. And it turns out that thing is related to an SL2R structure where you have, so imagine you have an SL2R matrix A, B, C, D, but all four entries are operators now. That's basically what this Q deformation is doing. Then in many papers from Teschner and collaborators, they argue that these operators should be positive operators. So the operator A, B, C, and D should have positive spectrums. And then if you take a classical limit of those kinds of statements, you would just get a matrix, an SL2R matrix A, B, C, D, where all four entries are positive. And that is defining the sub-semi group structure. So the match as a classical limit of these kinds of arguments was one of our motivations. I'm not sure if you follow that universal cover story, how these things would work out. So there's this Q deformation story, because then you would need to understand the quantum deformation of this specific limit of the universal cover. So that, I don't know, that would seem very hard. Or I'm not sure if that is understood, at least. So yeah, but as far as we know, at least for ordinary JT gravity, there seem to be two perspectives, and we have talked about this on the differences and so on, but we can't figure out which one is right, let's say, or they're both right, or there seems to be things that work nicely in one approach and things that work nicely in the other approach. And,
yeah.
You know, we definitely all agree that it's not just SL2R.
Right, yeah. Yeah, it has to be changed a little bit.
Unfortunately, yeah. And the main problem, and that was our initial confusion for a long time, is that if you really look at the irreducible representations of SL2R and you look at the continuous one, the Plancherel measure for that one is k times a tanh.
Tanh, yeah.
Yes, and not a sinh. And you need to somehow explain why there's a sinh here and not a tanh.
Right.
And these two modifications each seem to do that somehow.
Right, yeah. Yeah. So are you considering a similar semi-group thing for the supersymmetric BF theory?
Yes. So we're trying to figure out how things work for just OSP1/2, trying to construct basically the analogs of these Bessel K functions that we have here. So trying to do these representation matrices, and then doing that integral and getting the analogous thing that JT supergravity has. So that is at least what we're trying to do.
Gotcha.
I'm not sure what you're trying to do or in what direction you are thinking.
Yeah, so I'm trying to do basically the other perspective,
the universal cover?
The universal cover, yeah. Actually, so we had Luca Iliescu talk last week.
I see.
He didn't talk about this, but I asked him some questions after the seminar. So I have a better idea of where I think I should go. He's considered higher amounts of supersymmetry in their like perspective. So I think they're doing like 2,2 right now.
Yes,
but not n equals 1. So they're using a different supergroup.
Is there math literature known on the universal cover of OSP1/2 and so on?
I haven't seen any.
Because you need the generic Plancherel measures in that case, and that
I'm working through the basic group theory stuff now, so we'll see how far it gets. There's information about like the Haar measure, so I was hoping maybe I could.
Yes, but I don't think it's related. The Haar measure is on the group manifold. This measure is on the space of representations.
Oh yeah, well, so I don't know if have you seen Kitaev's paper notes on SL2R?
Yes.
Yeah. So you use the Haar measure to compute the Plancherel measure in his like rather brute force.
Yes, but you do it by actually doing an integral like that, right?
Right, yeah.
So you take two of them instead of three, and then on the right-hand side, you need to get a delta function divided by the Plancherel measure.
Yeah. Yes.
But you still need the knowledge of these things, these objects as well. Right?
That's fair, yeah. You still need the matrix element functions, yeah.
Yeah, but it sounds hard in any case. If you want to do this universal cover.
Yeah.
It sounds hard.
Well, it might not work out, but I'm certain I'm trying.
Well, hopefully there's literature.
Yeah, I mean, I keep finding new things that somehow I hadn't seen before in similar searches. So, like, I don't know. Yeah,
but it sounds very interesting if you're able to sort of push that story all the way to its end. Yeah.
Yeah, I mean, it'll be interesting to compare, assuming that things work out for both of us. It sounds like things are going pretty well for you. So.
For this supersymmetric case, it seems like we have all of the relevant objects there for the story, but there are always things that don't seem to perfectly match. So whenever there's one calculation that seems to make sense, then there's another calculation that is getting in trouble again, and so we're sort of chasing around in circles. But,
certainly, I think it sounds like you should make sure you have each other's emails to continue chatting, because it sounds like you're certainly thinking about the same kinds of things. Probably we should. If there are no more, what do you think? Should we continue chatting and recording, or should we?
You should definitely stop the recording.
Right.
So let's officially finish it by thanking Thomas again for a very nice talk.
Thank you.